We are in section 1.2, analyzing graphs of functions. Okay, so we're specifically going to be talking about functions today. With functions, we have two important things, the domain and the range. For the domain, you need to analyze the x values that are used. And for the range, you're going to and just state what they are, and then with the range, what the y values are. So in this first example, I have a graph, and this is a graph of a function f, where y equals f of x. And I'm asking you three questions about this. First of all, what is the domain? So to analyze the domain, you have to look at the graph specifically. This is the graph here. That was an open circle there. And it's at 0, 2. Okay, and so we're going to read, in this example, we're going to read off the x values that are used. So what x values do you see? Well, the first one, this is a closed circle here, is happening at x equals -3. So we start with -3. I'm going to go ahead and use set notation here, or interval notation, because that's what I like. And then you can see that the graph goes along this horizontal line until when x is -2, and then there's an open circle. But we pick right back up again at still when x is -2. So all the way up until -2, I'm using x values because we see graph there. And then we follow this line all the way up to 0, and then we have an open circle there. Then I have a jump in the x's from 0 to 1, and there's no graph between 0 and 1. I sort of have some scribble here, but there's no here at where this hole is supposed to be, but there's no graph here between 0 and 1. So I'm going to stop at 0, and 0 is a hole, so I don't include that, so I'm going to use a parenthesis. And then I pick back up again at 1, so I'm going to use a bracket there because, again, I'm using when I see graph at x equals 1. And then the graph continues on forever, infinitely up and to the right. And we always put a parenthesis around infinity because it's not a number. And so there was sort of a jump here between 0 and 1 in which no x values were used. All right, so what is the range? Well, the range, we're going to do the same thing, but we're going to determine the y values. The bottommost piece is here at -3. So it looks like I use -3. I'll use a different notation for this. So y equals -3, but then I jump up again. So I don't use anything between -3 and -2. But y is -2. Y does equal -2, and then this line here, y goes all the way up until 2, but we don't ever equal 2. Oh, wait, yes, we do, because the graph picks up again right here at this, right there at 1, 2, and then it goes on forever to infinity. So y is greater than -2. That encompasses all of those second two right pieces. Okay, and then the last question is, what is f of -2 and f of 1? And so the way we read these are the x values, the inputs, and we read out the y values. So f of -2, when x is -2, y is -2. So f of -2 is -2. And when x is 1, that's this piece over here, y is 2. So f of 1 equals 2. And you're just reading these two green points, you're reading their y values, and the x values are in the question. Okay, and then our next example here, I believe that this is an example that you are familiar with. This is determining if a graph is a function if it passes the vertical line test. So I'm going to let you do these two questions. I have two questions, A and B, two different graphs. I want you to write yes or no. This graph represents a function. Okay, next topic, we're going to talk about the zeros of a function. The zeros of a function. And there are several words that mean zeros. Also, these are called x-intercepts. These are also called roots. And I believe that's it. So our book tends to use the word zeros. So find the zeros of each function. That means you're going to set these equal to 0. You're going to replace the y value or the f of x value with 0 and solve. So I have 3 examples here. We're going to make y 0 and solve for x. Whenever you have a quadratic and you're solving for x, you have to factor that. This does factor as 4x plus 1, x plus 1. And now we set each factor equal to 0. This only works, by the way, when 0 is on the other side of the equation. 0 is special. Only 0 works for this. So negative 1/4 is x here, and here x is negative 1. So this f had 2 zeros. This was A. Now on B, we have G. And to find the zeros here, I'm going to set the square root of 8 minus x squared equal to 0. Square both sides. That will eliminate my square root. So 8 minus x squared equals 0. And now that means that x squared must be 8. And so x is plus or minus radical 8. It's nicer to write that as 2 radical 2. And finally, the third example, I'm going to just pull it down here. See, we have h as a function of f. I'm going to set this equal to 0. If a quotient or a rational expression here, we have a fraction, equals 0, then the numerator is 0, but the denominator may not be 0. Okay? You don't want the denominator to be 0. So if I solve, I get a solution of negative 1/3, and then you just want to make sure that this solution does not make the bottom 0. It doesn't. So that's my answer. All right, next topic, we have increasing, decreasing, constants, relative min, and relative max. Okay, so in example A here, I have a graph. Kind of went a little too far there. And we're going to determine where this function f is increasing, decreasing, constant, and then any maxes and mins. All right, so to start with, let's say where we are increasing. Increasing means that the graph is going up, right? So you can see that the graph would be increasing from here to here. By the way, you always read from left to right. So you want to think about if I were walking along this graph, walking, walking, walking. When do I go uphill? That is when I'm increasing. And that would be from this x value, which looks like it's negative 1.5, or negative 1.5. Until 0. You can include or exclude the endpoints, it doesn't matter. Then, next question, where am I walking downhill? Where is the function decreasing? Again, we're going to read from left to right. So I want to know when I'm going downhill. That's here and here. There's an open circle there. So that would be starting at negative 2, going until negative 1.5. And then also starting at 0 and going into 1. Then the constant was the next question. When is the graph constant? Well, you can see that a constant is when you're on flat ground, where I like to run if I run. Nice flat ground, I guess, if I can't go downhill. Then that would be on the interval starting when x is 1 and going out until infinity. All right, then on B, oh wait, so hold on, we haven't done maxes or mins. So relative maxes or mins are when you're at the top of the hill or the bottom of the valley, or the crest or the peak or the bottom, the valley. And so where is that on this graph? Let's see here. You can see right here is 1. So the minimum, wow, I shouldn't write in yellow. Minimum is at negative 1.5, comma, looks like negative 2. The actual minimum value is the x value, by the way. And then the maximum, use purple. It will be the height of a hill. It doesn't have to be overall the biggest or overall the smallest. And the maximum here would be 2. And then it happens at x equals 0. But the actual maximum is asking for the highest value, and it's a y value. So minimums and maximums are actually y values. and they occur at x values. But you can always just give me the entire point and you're covered, x comma y. All right, and then B, here's one for you to do. It's actually the graph of y equals 1 over x, and I'm going to let you finish that one on your in your notes. Next topic is lines. Lines. So I want you to graph the equation, or graph the line that this equation that is given by f of x equals negative 2/3 x plus 6. I think that, yes, I have an XY chart here. So I'm going to use this graph paper. You don't have to use graph paper. But to start off with, remember, this is the y-intercept. And that's what you should start with. Your y-intercept, where we cross the y-axis. That's going to be at 6. 1, 2, right here. And then the next thing I want you to look at is the slope. Okay, so the slope is negative 2/3. That means I'm going to rise, say, negative 2, and then run positive 3. So I'm going to make the rise negative 2 and the run 3. So if I rise negative 2, that means I'm going to go down 2, and then I'm going to run 3. We're going to always run in a positive direction to the right. And so my second point on the line is at this coordinate, and once you have 2 points, you've got a line. And don't draw dinky graphs, okay? Draw a big graph that takes up the whole screen. All right, next question, write the line. Okay, so this is a coordinate point. This is the point 2, 9. X is 2, y is 9. And this is the point 4, 17. To write the equation of a line, you need to have 2 ingredients. One is the slope, and then the other one is a point, any point at all. We have 2 points here, but we need the slope. So to find the slope, I'm going to do change in y over change in x. Just keep your first point the same. So let's make this the first point and this the second point. So I will do the 17 minus 9, change in y values over the change in x values. Over 4 minus 2. This is 8 over 2, that's 4. So I have a slope of 4. Now I'm going to use a formula. This is a formula for making equations of lines. It's important to know you're going to be doing it a lot this year. Y minus y1 equals m times x minus x1. This is called the point slope form, and the slope, m, is what we just found, the number 4. So I'm going to stick the 4 here. And then x1, y1 is a point, which we've got 2 of them. I'm just going to go ahead and use 2, 9. It doesn't matter. 2 I'll call the x1, and 9 I'll call the y1. And that goes here and here. You want to keep this y and x there, because we're making an equation of a line. It needs the variables y and x, so nothing is supposed to go in those. All right, so my answer is going to be y minus 9 equals 4, x minus 2. You may keep it there. You do not need to simplify. I will take that as full credit. All right, next topic. And then we have, I think 2 more after that. So we're on the greatest integer function. This is a function you've seen before, but I just want to reintroduce you to it. It's called the greatest integer function, but you're actually finding the greatest integer less than the number that you see in the brackets. All right, so what is the greatest integer less than 3.2? That would be 3. What is the greatest integer less than 4? Well, there isn't one. We don't want less than. It also could be equal to. So that would be itself 4. All right, now be careful here on the negative 1.2. The greatest integer less than negative 1.2 needs to be an integer smaller than negative 1.2. So if you think about a number line here, okay, and this is 0, here's negative 1, here's negative 2. Negative 1.2 is between them, right? So the closest integer less than it is negative 2. Sometimes people just think you round to the smallest, or you round down, but it's not round down. Greatest integer less than. And then here, this 3.99999 is so close to 4, but not quite 4. So the greatest integer less than that is 3. Okay, so with the greatest integer function, we need to know things about the graph. We're going to graph it. All right, I'm just going to plot it on these x values. Okay, so the decimals here between 0 and 1, those are going to round down to 0, including 0. But 1 will not. 1 will, when you do the greatest integer at 1, it will be 1. And so I'm going to jump up here. And then all of these values between 1 and 2, the greatest integer less than those values is going to be 1. And then at 2, I'm going to jump up to 2. And then, so this is also called the step function because the graphs look like steps. Now, oops, sorry, this is the y value negative 1. So between 0 and negative 1 and 0, these x values are going to round down to negative 1. And then at negative 2, you will get negative 2. But then the x values between negative 1 and negative 2 are going to round down to negative 2. Sorry. All right, so step function, you can see that. So what is the domain? All reals. You can plug in any x values that you want. But the range are only integers. So the set of all integers. I'm just going to write it out. Integers. You never get a fraction or a decimal, just like we like. All right, we're going to graph a piecewise function next. And I am going to go ahead and use a nice pretty graph again. All right, so this graph has two pieces. One is a line, and the other part is a square root. I'm going to start with the line. All right, the line is for x values less than or equal to 2. Here's 2 right here. Then the square root graph is for x values greater than 2. And so at 2, right here in this spot, we're going to switch. We're going to have different pieces. Okay, so let's just do this left piece. You can always plot some points, but this is a line, and I always recommend that you plot this point. So if I plug 2 in, I get negative 4 plus 1, that's negative 3. So 2, negative 3 is right here. I'm going to go ahead and fill that in. Then I'm going to use x values less than 2, so let's try 0. I'm going to go ahead and make a table here. So I did 2, and I got negative 3. And then I'm going to do 0, and here I'll get 1. So the point 0, 1. This is a line, so I'm going to go ahead and make a line. Now, normally you would extend over here too, but I don't want you to do that because we only are going to graph this line at the spot where x is less than 2. This is 2. This is where x is less than 2. And so I'm supposed to only see the line to the left of this line right here, which is not part of the graph. Okay, then let's graph the square root of x plus 2. I'll do that in green. So again, I still want you to try 2. So if x is 2, you would get square root of 4, which is 2. But this is in the square root graph. This is not actually a point. This is a hole. But I want you to plot these holes. So at 2, here I get a hole at 2. And the reason why that's a hole is because you wouldn't have a function, you wouldn't pass the vertical line test if that was an actual point as well. So it was defined well, and it will always be that way. Otherwise, it's not a function. All right, now let's pick another value greater than 2. I don't want to use 3 because then I'd have the square root of 5. The next nice square root is square root of what? Not 4, but 9. And that will happen at x equals 7. So at 7, I would get square root of 9, which is 3. So 2, 3, 4. And then I have the value 3. And then I know square roots look like this. All right, so let me just clean this up a little bit and show you what the answer is officially without all of this extra stuff. Okay, so the answer officially is going to be this black picture right here. You want a hole in this piece right here because we have a not equal to there. But wait a minute. Sorry, that was at 2, 2, which is there. I might have had that in the wrong spot before, but at 2, 2, right? My point's 2, 2. Oops, there it is. All right, so that's graphing piecewise functions. Last thing we're going to talk about, I think, yes. Last thing we're going to talk about are even and odd functions. And we've already talked about symmetry a little bit, so this is going to be a review. So a function is even if, technically, if you replace the x with negative x, you get the same output, f of x. Even functions are symmetric to the y-axis. And then we say a function is odd if when you input x, negative x, you get out f of negative x. Sorry, hold on. Too many negatives. You get the opposite of what you started with. Okay? Also, this has both even and this has both x and y axis symmetry. And so you can test the old way where you replace x with negative x and y with negative y. I'll do that for you on an example that's odd, which would be this first one. Okay, so we have 3 last examples here. This is going to be odd. Let me show you with the new way with function notation. So I'm going to replace x with negative x. All right, this is negative x cubed plus x, which is way different from the original, but it's an interesting way of different. The way in which it's different is if I take out a negative, then I get the exact opposite of the original function. This is negative f of x. And so this is odd. The other way of checking this is you can go back to what we learned previously with x and y, where we weren't talking specifically about functions. F of x is the same as y. So here I've replaced the question's f of x with a y. And now I'm going to test for origin symmetry. I'm going to replace y with negative y and x with negative x. So this is the second option. You don't have to do both of these. Then I get negative y equals negative x cubed, I forgot it there, plus x. And then if I multiply both sides by negative 1, then I get y equals x cubed minus x, and that's the original. And so I have, again, origin symmetry, or we say my function is odd. So odd is the new word. All right, G and H, I'm going to leave up for you to do just before you come to class in your notes.